And yeah, so this is a very lightweight, non-technical overview of sort of the priorities and focus points of the Co-dfns compiler. And we have a lot of new people or people who haven't been around for a while that are coming back. And so I've noticed a lot of people are doing an intro to themselves, but I was asked this late last night, and I didn't have an intro slide, and I couldn't help myself, but I thought about it a little bit, and I couldn't help but think of an answer that would have been appropriate last night for, But I can introduce you to the Co-dfns compiler and give you a little bit of a background on what we're dealing with, why the compiler exists, what we're trying to achieve, status, and all that good jazz. So at its heart, if we think about what the compiler is in general, it's just a compiled implementation of APL that supports multiple hardware platforms. We try to make it do things that are hard to do in the interpreter, so do static analysis through it, support a variety of execution workloads, things like that. We have a flexible backend design to try to improve the portability of the implementation, and we're kind of targeting a low overhead, high productivity type of APL. That's kind of our goal, is to really reduce the overheads associated with running and executing over APL. And one of the things that has become really important is our ability to flexibly integrate into environments that you might not otherwise be able to use APL for. And what that means, we'll talk a bit about that more. So in the course of developing this, it's also true that Co-dfns serves as a sort of guide or manual to a certain suite of APL programming techniques that might otherwise, you might not be exposed to without this kind of stuff. So for instance, it's probably the largest application using this set or suite, or heavily using these set of tree manipulation techniques in APL that I've been spending a lot of time developing. And it also serves as a sort of alternative example of architectural design, particularly austere type, that tries to remain really simple. And because we're working on problems that maybe are not always the typical APL problems, the APL code can serve as examples of maybe different ways to approach problems and optimize problems that you're writing in APL, different styles. That includes things like different ways of parallelizing your APL code, coding styles, and it serves as a sort of demonstration of what you might be able to achieve with APL using low abstraction programming techniques, as opposed to really, really heavily engineered methods. So the goal is sort of to make a tool that allows for APL to scale in a lot of different dimensions, and that initially you're talking things like apply it to different problems. So maybe you want to be able to work on domains that the interpreter is too slow for, or something like this, or help improve your performance in your hotspots. Or maybe you want to execute on GPUs or CPUs or FPGAs or something like that. These are all sort of our target goals. Or maybe you want to integrate APL into an environment where the interpreter doesn't go as far. And because of the architecture of the compiler, we can do a lot more experiments and play with design a little bit more and be a little bit more flexible than the interpreter in terms of language design and features that we provide ad hoc. And that leads us to a set of 4 basic use cases for the compiler and what we're working with. So the number one use case that most people will be familiar with, and which is the most maturely developed in the compiler, is executing APL on the GPU. Now, the GPU does really well with certain types of workloads, but if you don't know how to program it, it kind of becomes a really big beast that's annoying. But as an APLer, you have an advantage, because the rules for writing reasonable GPU code it actually maps really well to writing a certain class of reasonable APL code, primarily working over large bits of arrays that all are manipulated with your core APL primitives. And these would be things like your heavy data crunching applications, things where you might have a really computationally expensive algorithm that you can express using these core primitives, and where you've got potentially a lot of data to churn over, or a lot of computations that you need to compute. So these would be like your kernels or your hotspots. So not necessarily your entire application, but places where you can write up the math. You might think of it as the place where you might be a little math heavy, math and data heavy. So places that we've seen this work well in the Co-dfns compiler so far are things like simulations, LLMs, time series type stuff, doing graph computations. All of those are reasonable targets to think of for this GPU use case. And we've been doing that for a while, but there are also a lot of APL programs out there that are written in this very scalar style, right? And some of those actually cause significant performance drain on the application because they might have a lot of small utilities, and those utilities might be called really often, and those utilities or that scalar code might end up inside of some computationally important inner loop somewhere. And if you have a little bit of extra overhead on these all the time, well, that can cause a lot of problems and slow you down. So there's a compiler that Dyalog provides inside the interpreter that Jay Fode wrote, which can help reduce the overhead of the interpreter on some of these kinds of problems. And we're kind of looking at can Co-dfns also provide a similar benefit through improving or reducing the interpreter overhead via compiling these little pieces of code. But that requires a different type of back-end target generation. We have to pay a lot of attention to how our memory is used and how much it costs to execute a single thing, rather than just applying these big, giant optimized primitives over everything. And of course, I think you've heard from Brandon already, the parser for the Co-dfns compiler is its own API, and you have access to the intermediate representation that we use within the compiler as a user of the compiler. And so the design of the parser is that we are trying to make what's called a static offline parser. So that means you don't have to start executing your code in order to see the AST. And the benefit of something like that is that rather than executing your code and sort of on the fly having to dynamically check things, you can get that source code, get an AST out of it, and then ask questions about your source code in a sophisticated way. You don't have to just use like grep or regular expressions or something to find things in your code. You can do more sophisticated linting and traditional static analysis to find other problems. So I think Morten gave an example of like looking for cases where you're using a stranding and then bracket indexing on that strand, or maybe you want to write something that lets you find all of the semi-glottals that shadow this one variable inside of a Trad-fn somewhere. That kind of thing would be a useful thing that you'd get static analysis out of. And while this is helpful for writing things like security auditing software or other sorts of traditional static analysis, additionally, if you are trying to refactor code or migrate code from one place to another, it can be really useful to have a richer representation that you can explore to find potential areas that you need to focus on or look at while you're doing those migrations. And the fourth use case is that sometimes, well, we run into this problem where sometimes a potential APL customer needs to deploy APL in a very hostile environment. And this might be a place where, or it might just be a technically hostile environment where it's difficult to run the interpreter. And this could be as simple as, well, they've got a rule in my company that I'm not allowed to distribute an interpreter with my application. That has occurred. Or it might be that we want to run in the cloud on a JavaScript client side or something like this. And it's very hard for the interpreter right now to run in the browser. So theoretically possible, very difficult. Not really something that is too easy to do. But with the compiler, we have a lot more control over the types of code we're generating, and we can limit what we do or constrain it, or we have a lot of control with this back end, which then allows us to maybe target some of these environments. If you've got an embedded environment and you're not allowed to use the allocator, so there's some customers in like aerospace and stuff like that where you can't distribute the full runtime memory system. So you need something that's really stripped down, and you need to be able to provide guarantees around that. So right now, JavaScript and WASM and embedded apps are probably the highest priority here. But if you've got another place that's hostile that you would like to deploy APL for, this would talk to me. I'd like to make sure that we can provide that for you. So a lot of this stuff becomes useful for more than just what Morten calls the functionistas, right? The people that are doing modern functional programming on places. You can right now, the compiler tends to focus on functional-oriented programming on dfns. But there's a lot of traditional APL features that we might want to access because that can improve your integration for these other domains and these other use cases. And sometimes Trad-fns can provide really useful dynamic features that you want to leverage. And we would like to take advantage of that even in some normal, typical cases. But supporting all the traditional APL features has never been an explicit goal of Co-dfns. And we split right now. The way we're looking at supporting these traditional features is to split the support into two categories. And the most support would come from what we call this executable support, where we will compile this feature and you'll be able to produce executables or link it into the workspace or anything like that and run code that is using these features. Or some of these features, we will support static analysis and parsing on it. So you'll be able to get an AST, you'll be able to do things with that stuff, but you won't be able to compile and run it. You'll be able to ask questions, query, see the AST, things like that. So the biggest one is that we're not currently planning on providing compiled support for the whole object-oriented class system in APL and Dyalog. We would plan to provide parsing support for it, and parsing support for things that you need to do the Win32 and the .NET, HTML renderer, some of the interpreter-specific quad functions, and features that might be in non-Dyalog dialects that can support migration, that we plan to support in the parser. But for executable support, we're really kind of focused on things like Trad-fns, gotos, structured statements, nested namespaces, execute, these dynamic features, and not this suite of OOP-oriented stuff. And when it comes to the parser-only supported features, you can sort of rely on the idea that you'll get a valid, viable static AST, and the parser and system will be aware of these features when it has to do things like name resolution and control flow analysis, but you won't get any executability. So Trad-fns is the big sort of, what you've got a bugbear is one of your favorite words, Brandon. The Trad-fns introduces a whole suite of problems for us, primarily for the parsing, because it has dynamic scope. And that means that there's no way completely to eliminate the possibility that you've got inherently broken code in your system. Because there might be code that you always only ever run in one way, but can always, at least in theory, be run in another way that will break the whole thing. And that's true with Trad-fns sort of inherently because of the dynamic scope and how it works. So, you can you can introduce all sorts of issues here with that kind of stuff. And we have been spending quite a bit of time trying to come up with reasonable approaches to this. And after looking at a lot of the potential cases, things we might want to do, we've come up with an approach that we're going to pilot for this that's partially or mostly implemented at this point. But it's important for us that we get your feedback on how well this would map to code that you care about in these cases. And if it doesn't map, we need to know about it because we have other approaches we can take, and they have different trade-offs. But this is the one we want to start with, and then we want to make sure that you guys communicate to us whether or not you're going to need a different interpretation of the Trad-fns. So right now, the model we're looking at is what we're calling like lexically compatible Trad-fns. And that doesn't mean that they're lexically scoped. It just means that you don't change the name class of a variable via shadowing. Right? So if you have something that appears in the top level, it doesn't suddenly become some totally different name class somewhere down in terms of effective name class. So that means there's some leeway there. It's mostly just things that can be thought of as arrays or niladic functions, and things that can be thought of as functions or dyadic or monadic operators. And if you can guarantee that, you can get what's called a statically computable call graph, and then we can have things like shadowed variables and semi-globals and dynamic scope and lexical global scope, and it all basically works. But it requires that we have this lexical compatibility for this model. Now, if that's too restrictive or doesn't work for you, or if you've got places where you think you can break this, send me some example pieces of code if possible, or just talk to me about it so that we can adapt this approach for whatever your code needs to be. And that's not quite far enough to handle certain extra cases, so we also are allowing you to parameterize the parser with additional type information if you want, which will allow you to sort of hold the parser's hand a little bit and tell it, no, trust me. this is really how it works, and then you can get some good answers. And that will also be one way that you can expand what you do with the parser. So as a current progress report on this, our efforts are unfortunately spread across more domains than I would like. I would prefer to be focusing on one of these things, but we're kind of having to do all of them. But the static parser is what is taking up a lot of time right now. We're working on reducing the memory overheads of the system. That's the sort of to help use case number 2 with those getting rid of the interpreter churn, but it also helps everywhere else because the compiler compiles its own runtime. So if it compiles things slowly in the runtime, that costs everybody something. So we've made a lot of headway there. We continue to improve the algorithms, the GPU algorithms that we're running, but we're also working on getting code generation to work on other platforms like JavaScript or Python, C#, Rust, that kind of stuff, and working on, so that requires some other internal compiler optimizations. And we're doing a more expansive benchmarking effort now that we're expanding on. So progress on the parser, the Trad-fns support is a really big one that's been taking up a lot of time. That's mostly complete, or an initial early version of that is complete now, but we've sort of got the tokenization for all of these other features in place as well. And we're working on the memory overheads, but memory overheads get really, really, really super geeky really, really, really fast. So if you're curious about that, I'd love to talk about it. But I'm not going to talk about it in the talk here. And we've made some performance, but a lot of that is because it started slower than it should have been. So 30x on bad isn't good. But we've probably got another 30x or 10x to work on above what we've got right now. And our goal is to sort of reduce or eliminate these memory overheads entirely. And we're working on sort of this set of benchmarks right now. This is sort of the suite of them that we're trying to get solved. And some of these we've got a paper in the works that we're going to be trying to publish on the results of benchmarking those against both the interpreter and other array language solutions that are out there right now. And typically what we're seeing compared to the Dyalog interpreter is somewhere between 10x, on that band, with the low end usually being 2 or 4x performance, and then sometimes when you get lucky, you can get way higher than that. Faster. This is speed up. Yeah. There are occasionally very perverse places where you can try to find a good Dyalog being easily outperforming the compiler for specific cases, but we're trying to make sure that doesn't happen. So my recommendations right now are version 4 is still, if you want to do the use case number 1, the GPU algorithms, and you've got those flat computations that you work over, version 4 is still the best way to go. We've got some issues compiling on Mac because of this transition over the architectures. It's a real pain, so if you're on Mac and you feel very brave, come talk to me. Otherwise, we're working on it, and it'll get fixed. Version 5 and above, that's where most of the additional features are going in. This is if you want to, for instance, mix and match CPU and GPU execution, and you want to get access to extra features and things like that, you kind of have to be on V5 Plus. There's no other option. We still do not have, but we intend to implement error guards and selective assignment, but those are still the biggest sort of missing features in the runtime as it exists right now. But there are some unique features that the compiler can give you that sort of may be rare or don't exist in other places. So one is you can sort of produce self-contained EXEs that are entirely independent of anything else on all of the platforms that we can compile to. And eventually that will also be possible on the Mac, so you don't have any other dependencies sitting around. You can get a really, really, really high degree of integration with your backends. And that's C right now, but as other backends come up, you'll have the ability to extremely tightly couple with other platform spaces through this agnostic foreign function interface, and that in a way that completely eliminates any executive overhead that you might have. So there's no pipe that's communicating between two execution platforms. It's executing just natively raw in whatever your underlying environment is. And we have the ability to do a lot of extensible runtime implementations for new operators or new functions, or your own functions and operators. You can support that and integrate them into your own stack. And unlike a lot of other systems, Co-dfns is dual licensed. I've had a couple of questions about this, where if you are already a commercial licensor or a free licensor of Dyalog, you can use it under the Dyalog license, and you get it, and you sort of just have access to it. But if you need to integrate with an open source ecosystem, it is AGPL compatible. And so you can use the Co-dfns compiler in runtime under an AGPL license if you would like to integrate into places that are open source only, for instance. Now that also means your code kind of has to be AGPL, and you need to consider whether that will be a viable license for you, but that's at least an option. So thanks. I think I got under time, which is nice, and I'll take any questions if you have.